All right, so now we're starting something new, something that's kind of goes away from kinematics, and we start talking about forces. We can still incorporate the ideas of kinematics into this unit, but we get a little bit away from the kinematic equations. We don't have to use them as often, but they still exist, so we can't completely ignore them. The idea of forces is best introduced by going through the laws of motion, Newton's laws of motion. And we break these down into three: first, second, third. We'll start with the first law and probably test on that. And then second law, we'll test on that. And then third law, which doesn't take nearly as long, we might have a shorter quiz on that. All right, this concept of inertia, something that we need to talk about if we introduce forces. Inertia, first off, inertia itself is not a force. Inertia is just a property that an object has. And we see that it says it's the property of an object to resist a change in the state of motion. In other words, the more inertia something has, the more it wants to resist being accelerated. And we already know acceleration means speeding up, slowing down, or changing direction. So if you're trying to do that to an object, and it's really difficult to do, like a car or a boulder, that object has a lot of inertia. And we see there's a direct relationship between the inertia something has and the mass something has. So mass is a measurement that we can use to say if something has a lot of inertia or not. More mass means more inertia, means more resistance to acceleration. We see inertia every day. You don't think about it, but it happens all the time. Inertia is the reason we wear seatbelts. You're driving along, you come to a quick stop, your body wants to keep moving forward because it has inertia. The seatbelt is there to prevent that from happening. Headrest, the same sort of idea. When you're at rest and you hit the accelerator, your head goes back, it hits the headrest. The headrest wasn't there, you might get whiplash in your neck or something. Passengers standing on a bus or a tram, like MARTA or something, it's very easy to stand up without holding on to anything until the train speeds up or slows down or goes around a curve, meaning changes direction. When we shake a ketchup bottle and we want to get the very last little bit, we shake it downward and then we bring it back up quickly. And that means that the ketchup that's in there that was at the bottom of the bottle, when we reverse the direction quickly, the ketchup that was in the bottle wants to continue to move in the direction you were moving at first. Air hockey table. You think about the puck on an air hockey table. You barely tap it. It keeps floating and floating and floating along that very thin layer of air and bounces off the sides. But it keeps on moving in a straight line pretty much until something acts on it, like the end of a table or something that you're holding to play with the puck. When you fix the head of a hammer, it's easier to throw the hammer down with the wooden side facing the table instead of the metal side of the hammer. When you do that, you hit the table. The hammer head, which has much more mass, wants to continue moving towards the table. So that causes it to fasten itself onto the wooden handle, much easier. A paper towel roll, if you want to grab a paper towel roll, a single paper towel, you jerk it really quickly. And the reason you jerk it is because the paper towel roll has a very large, well, not large, but it has some inertia. And when you rip or jerk on the paper towel piece, you break that you break the perforated part, and the paper towel comes off. Same thing happens with bathroom tissue paper or whatever. Obviously, when you're at Kroger or your Publix and you have a very heavy shopping cart full of all the stuff you're going to buy, and you want to go from aisle 11 to aisle 12, and you try to make that turn, it's very difficult to make that turn with a full shopping cart, as opposed to maybe from aisle 1 to aisle 2, you hardly had anything in it. Very easy to make the turn because in that case it has less mass, therefore less inertia. So what is a force? We haven't really talked about forces. We've mentioned them, but we've never really truly defined it. It says the ability to cause a change in the state of motion of an object. The presence of a force doesn't mean there will be a change in the state of motion of an object. So it's the intent to cause a change in state of motion of an object. A force is something you use to cause an object to accelerate, to make that object change its current state of motion. If you have an object that is stationary and you go to pick it up, you are changing its state of motion. You are causing it to accelerate. If there's an object that's rolling along the floor, like a ball or marble, and you reach out to stop it, you are changing its state of motion. If you hit a tennis ball with a racket back to your opponent, you are changing the direction of the ball. You're causing it to accelerate. So anytime you cause an object to accelerate, or you intend to cause an object to accelerate, we say you're using a force. For example, if I push on a large cinder block wall, like in my classroom, I can apply a force to that wall. I'm trying to move that wall, but it's not going to move, yet I'm still applying a force. So what's resisting my pushing? Well, the wall is pushing back at me, believe it or not. That's a little third law concept. So we say that force, mass, and acceleration, they're all related, and they're actually related together in a formula that we call the second law. We already know that mass is a measurement of the tendency of an object to resist acceleration. Bigger mass, more resistance; less mass, less resistance. And yes, force is a vector quantity, just like acceleration was, just like velocity was, just like displacement. It is also a vector quantity. So it has a magnitude and it has a direction. And it's always the interaction between two different objects. Types of forces. There's two broad types of forces. There's what we call contact forces, and then what we call field forces. Contact forces, as the name implies, is forces that are used where there has to be direct contact between the two objects. So if I'm applying a force by lifting up a box, I have to take my hand, I have to touch that box, I have to contact it and lift it up. I can't just look at it to make it move unless I'm Luke Skywalker or something. Air resistance force, if you take your hand and you put it out the window, you feel the air hitting your hand. That's direct contact between the air molecules and your hand. Friction force, if you're trying to slide an object across the floor, maybe you're moving your dresser from one side of your room to another, we say that friction force is a contact force between the two, the dresser and whatever the floor is made of, if it's carpet or wooden floor or whatever. Normal force we'll get into, but it's the force that a surface applies to an object. So if you have an object sitting on a table, like a soap dispenser next to a sink, the soap dispenser is applying a force downward on the table. We call that weight. The table itself, the surface that it's sitting on, is pushing up on the soap dispenser bottle. So we call that the normal force. We'll get into the idea later on. And then tension force, which is a force that has things for ropes, like pulling something or fishing line or something like that. And then field forces are when you have an action on an object from a distance. The two objects don't have to touch for there to be interaction between the two. So the force of gravity is certainly the first one that you would think of. If you jump off of a tree limb, you are headed to the ground, you are not in contact with the earth at that point, but the earth is still acting on your body with a force. It's pulling you down. The planets orbiting the sun, they are not in direct contact with the sun, but the sun exerts a gravitational force on the planets, preventing them from traveling in a straight line. The moon is by gravitational force of the earth orbiting the earth. No direct contact required. Electrical force, like if static electricity, there's a force applied to your hand when you get shocked on a doorknob. You don't have to touch the doorknob for the shock to make its way across. Same thing with lightning striking the surface of the earth. And of course, magnetic forces. We can use magnets to make things move without touching them. Magnets are used quite a bit in electricity. We say that's electromagnetism, but we'll get into that later. Well, just like every other variable we've discussed in physics, forces have a unit as well, and that unit is called the Newton. It's abbreviated with a capital N. You'll use this quite often in this course. And if we were going to relate it to, say, an English unit, like we say miles is a distance unit and kilometers is a metric unit for distance, pounds would be the English unit for force. So you can apply certain pounds of force by lifting up a box, but you also supply a certain number of newtons of force to lift up that box. And the conversion there is 10 newtons is equal to 2.2 pounds. So the first law, this is the standard first law definition that you would see in pretty much any physics book. It says an object remains at rest, an object at rest remains at rest, and an object in motion continues in motion with constant velocity. We say that's a constant speed in a straight line, unless the object experiences a net external force. So objects, we say, are lazy. We give them a personality there. We say that they're lazy. Objects like to do what they're already doing. If an object's moving in a straight line at a constant speed, it wants to keep doing that because it's lazy, because it's going to require something outside to cause it to change its direction. If an object's just sitting somewhere stationary, it wants to stay stationary. It doesn't want to move any. So we say that that's the first law. Objects continue doing what they're already doing unless something from the outside causes them to change their state of motion. And we call that an external force. Now, net force is really a combination of all the forces that are acting on an object. Okay, it says the combination of all external forces acting on an object. It says the net force of an object that changes the object's motion. It causes it to accelerate. Let's take this box, for example. If I were to apply a force to this box, let's just say it was 10 newtons of force. If I apply 10 newtons of force to the box, and the friction that I'm pushing against is 7 newtons. The forces are in opposite directions, and we know if they're in opposite directions that their signs are going to be different. So if I wanted to know the net force here, I could say the 10 newtons that I'm pushing to the right minus the 7 newtons that friction's going against me with. So my overall net force would be 3 newtons. So the red line represents what we call the resultant force. this idea of net force we'll get more and more into as we head towards the second law. But it can be confusing. If you think of net income, if you learn any economics, it may help, just the analogy. You get a certain amount of pay when you're working a job, and you get what we call the gross income. And what that means is that's the income that you get before anything is taken out, taxes, insurance, whatever. The paycheck that you actually receive, what goes in your pocket, is what we call the net income. So you might make $50,000 a year, $100,000 a year, whatever. That would be your gross income. And then whatever you actually put in the bank, let's say $50,000 is your gross, and you have $5,000 in taxes and insurance and whatever else they take out. So that would be $45,000 is your net income. Or if you make $100,000 gross and there's $10,000 of taxes and everything taken out, your net income is going to be $90,000. So that's what when we say net force, we're talking about what is the overall net force affecting an object. It's the combination of everything, all the forces acting on it. And what we'll learn here in a second is that net forces are what causes things to accelerate. If the net force is zero on an object, it's not going to accelerate. We say it's in equilibrium. Speaking of that, equilibrium, mechanical equilibrium, an object at rest or moving with a constant velocity is in equilibrium. I think it's very easy for students to see why something is at equilibrium when it's at rest, but they have trouble with this idea of constant velocity is at equilibrium. They feel like if something's moving, that there's got to be a net force causing it to move, but that's not the case. We just said that the first law, objects are lazy. They're going to want to do what they're already doing. So if something is in motion, and there's a car rolling down the street, and it's traveling at a constant velocity, that means that it's already at constant speed and it's already not changing direction, it's in a straight line. It wants to keep doing that. The only way that's going to change is if we take it out of equilibrium. And that means that we would have to apply a net force to it. Okay? So net force is zero if something is in equilibrium. And this is also important. Doesn't mean there aren't any forces acting on it. If I push on the wall doesn't move, and I say, oh, well, I'm in equilibrium with the wall, it doesn't mean that I'm not applying a force to the wall, or that the wall's not applying a force to me. If I push on a car and the car doesn't move, I'd say, oh, I'm not applying any force to that car. It's not moving. Well, that's not the case. If you're pushing on the car and it doesn't move, it's because the car is pushing on you just as hard as you're pushing on the car. So the forces balance out. We say they're at equilibrium. So it doesn't mean that there are no forces on something if it's at equilibrium. So we have this symbol that we use, this sigma symbol, and it means the sum. So I would read this: the sum of the forces equals zero. That's what equilibrium is. It's when the sum of all the forces on an object equals zero. So anytime you see that symbol, that means the sum of. And usually it's the sum of the forces. There are two types of equilibrium. There's static and dynamic. In both situations, the object is at equilibrium. Static equilibrium is objects at rest. Static equilibrium is when objects are not moving. Dynamic equilibrium is when the objects are at equilibrium, but they are moving at constant velocity. So this Jeep down here, the engine is applying a certain force as it's moving down the road. The friction of the road is pushing up, against the force of the engine. But if this Jeep is traveling at constant velocity, we say it's in dynamic equilibrium. But if the Jeep was just sitting in a parking place and it's not moving, we say that it is also in equilibrium, but because it's not in motion, we say it's static equilibrium. So they both mean the same thing. It's just static is an object that's sitting still and dynamic is an object that's in motion. All right, mass versus weight, definitely not the same thing. The unit for mass, the SI unit, is kilograms. The unit for weight is Newton, and this part here represents a kilogram meter per second squared. That's what a Newton is, but it's certainly much easier to write a capital N than writing all that, but that is what it represents. Weight is a vector quantity. It has magnitude with direction. Mass is not a vector quantity. It's scalar only, and it's magnitude. And mass is intrinsic, and weight is extrinsic. The idea between an intrinsic property is that an intrinsic property is not going to change regardless of the conditions that you're in. You have the same mass on top of Mount Everest that you would in Death Valley, but your weight is affected by external things, external circumstances. Because you're farther away from the center of the Earth, the pull of gravity on you is not as great at a higher elevation than it would be at a lower elevation. So you do have a different weight at the top of Mount Everest than you would in Death Valley. So weight can change depending on where you are. The formula for weight, and that is an F with a subscript W. The F stands for force, the W stands for weight, is equal to the mass times the acceleration due to gravity. So if you want to find the weight of any object, all you need to know is how many kilograms it is, and you're going to multiply that by 9.81 meters per second squared. Sometimes you'll see weight written as just mg. We usually in this course write it as FW, but you may run into it as mg at some point. This is actually based on the second law of motion, but we'll get into that later. But it's this idea that the kilograms, it's not the grams. If you're given grams and you're asked to find the weight of something, you need to convert those to kilograms. It's the kilograms times the 9.81 meters per second. And you hopefully can see where this comes from. A kilogram times a meter per second squared is a Newton. So as we were saying earlier, it's the magnitude, weight is the magnitude of gravity's force exerted on an object. So are people heavier in New Orleans than they are in Denver? Well, Denver is 1 mile above sea level, and New Orleans is below sea level. So if you're below sea level, you're closer to the center of the Earth. Gravity's effect on you is greater than it would be if you were in Denver. So technically, yes, you do weigh more in New Orleans than you would in Denver simply because your location changes. Your mass wouldn't be any different. Your mass of 90 kilograms, if that was your mass, would be 90 kilograms in New Orleans, and it would be 90 kilograms in Denver. It would be 90 kilograms on the moon. Wherever you were, your mass stays the same. Your weight differs depending on how gravity changes. The Earth is always pulling down towards the center. So whenever we draw the vector for weight, you'll always draw it straight down on your paper. So you may have an object sitting on the ground, and if we were going to draw the vector for that, we would draw it straight down. And we'd label it FW. Again, I told you earlier, some people would label that mg, but FW is what I tend to use more than anything, and that would be measured in newtons. So again, mass is not a force. You can convert it to a force by multiplying it by 9.81. So a bathroom scale, if you think about it, the bathroom scale, it's technically not measuring your weight directly, because what's happening is as you are on top, so here's the scale, right? You are on top of the scale and you are pushing down with a certain number of newtons. Well, the scale has to react to that. In other words, it has to balance out. Otherwise, if there's no force going against your weight, you would go through the floor. So the scale has to provide a force going this way. And since you're not moving, since it's balanced, since it's at equilibrium, whatever your weight is, the scale will provide that exact weight, force in the opposite direction. And we call that normal force, which we'll take on later. But that's the idea. When you stand on a scale, the scale is not reading your weight, it's reading how much force it has to provide to balance out your weight. So it's measuring your weight indirectly, kind of, if you think about it that way. Now, normal force is the force that says that a surface applies to an object. It's always perpendicular to the surface. So let's go back to our box. We have a box, it's sitting on the table. We know that weight pulls this way. That's the force of weight. Well, the normal force is always perpendicular to the surface. Well, here's the surface. So we would say it's 90 degrees to that. So we would draw our normal force vector directly opposite. And we would label it F sub n. That just means normal force. If there is no surface, you do not have a normal force. Okay? So an object that's in free fall, you say, oh, well, it's touching the surface of the air molecules. No, it needs to be something solid, something solid. So if you're on an incline, let's say, and you have this object sitting on the incline, like that. Well, this is the surface now. The box is sitting on this surface. So if I was going to draw the normal force for that, I would draw it perpendicular, 90-degree angle, to the red line. You would not draw it straight up like that. Okay? And of course, weight would still be straight down. Always straight down. Weight's always going to pull straight down on your paper. And if you're pushing on a wall with your hand, here's the wall, and you're pushing in towards the wall's pushing back, that would be the normal force perpendicular, right? There's a 90-degree angle right there. The wall would be, that normal force would be exerted by the wall on your hand if you're pushing it with your hand. So let's talk about friction. Force due to the fact that no surfaces are perfectly smooth. In a perfect world, we could have a no friction surface, but in the real world, everything is going to have, every surface is going to have friction. Even the smoothest ice you could think of is still going to have some friction. So a lot of times in physics, you'll come across a problem and it says on a frictionless surface. Well, this is of course a perfect world scenario. It's used to help understand these concepts of physics that we're trying to learn. But real world, we know that friction exists on any surface. So, all right, let's talk about friction. It always acts parallel to the surface of contact. So if I am working on pushing a box, let's just say, and I'm trying to, let's say I'm trying to push the box in this direction to the right. That would be what we call an applied force. Well, the rule is friction always acts parallel to the surface of the contact. So it's going to be either to the left or to the right, because this is the surface, and this would be parallel to the surface. And which way would we go? Well, the direction of the friction force always goes opposite the direction of motion or intended motion. So when we draw the friction vector, we're going to point it directly opposite the way the box is moving. And notice it says here intended motion. Well, if I was trying to push on a very heavy object in one direction and I just couldn't get it to move, I'm still applying a force. There's still friction there. So if I'm trying to move it to the right, friction force is going to be going to the left, even if the object's not moving. So I'm intending to move the box, but it's so heavy I can't get it to move. And there are two main types of friction. There's static friction and there's kinetic friction. We'll address each one of those now. So the first type of friction is what we call static friction. And it's the friction that you're going to encounter when you're trying to move an object and that object doesn't move. If we think of the word static, we think of, like, if you have static conditions in the weather, you think of air that's not moving. So static conditions or static friction is going to be when you encounter friction and the object is not in motion. So as you're pushing on a box, let's say, on the ground, let's say you're pushing again to the right, so that's your applied force. And let's just say this object isn't moving, this box isn't moving. I keep pushing, I increase my force to the right. Well, as I keep pushing harder and harder, the friction force increases as well. And because it's not moving, we call it static friction. So if I'm moving a very heavy dresser and I push on it in a certain direction and it doesn't move, and I push harder and it still doesn't move, and I push harder and it still doesn't move, the friction that I'm going against is increasing every time I try and push harder. Now there's a point that you're going to reach where the object will start to move. And as you approach that point, we call this static friction max, where it's going to max out, and just after it gets to static friction max, the object will start moving and start to accelerate. So if we have a static friction max of 10 newtons and I push with 10.1, I'm going to start that object moving because I've surpassed what we call static friction max. And static friction max can change depending on the mass of the object you're dealing with, the surfaces that you're coming in contact with. There are lots of things that can affect it. But it's a hard concept to get, because if you think about, let's just say I have the same box and I'm pushing even harder to the right, and I denote that with a longer vector. Well, as I push harder to the right, this friction vector gets even longer because it's increasing as I try and push harder and harder. So this static friction max can adjust all the way up until what we call static friction max. Once you surpass that, you cause the object to move, and it turns into a different type of friction, which we call kinetic friction. So kinetic friction is still friction force when the object is in motion. Notice here that friction kinetic, that should be a subscript, is less than friction static, always. And think about it. If you're trying to move a car, let's say you run out of gas and you're on a flat surface, and you want to start pushing that car to the gas station. It's much harder to get the car to start moving than it is to keep it moving. And this is the reason. The static friction max increases as you try and push the car harder and harder. But once you surpass static friction max and you convert to kinetic friction, the kinetic friction value is always lower than the static friction value, and this has to do with inertia. Remember we said earlier that an object that's already either at rest or already moving wants to keep on doing that. So once you get this car moving, what does the first law say? Well, it says that that car wants to keep on moving. So it's easier to keep it moving than to start it moving. Friction sometimes, for whatever reason, gets a negative connotation, but friction can be a positive force as well. It's the reason we can walk. When we push down on the ground and really in the opposite direction that we're going, we want there to be friction between our shoes and the floor so that we can continue walking in the direction we want to walk. If I push my shoes in that direction, I end up going in this direction. Think about it, you're pushing in the opposite direction that you're moving. You can find this out if you ever try to step off of a pier from a boat. There's very little friction between the boat and the water, and you certainly could find yourself falling in the water because you push the canoe away from you or the boat away from you when you try and step onto the pier. So certainly walking is a positive aspect of friction. We certainly want our brakes to have friction. We want our tires to have friction when we're turning on a sharp turn. When you're trying to open a lid, you typically can use something to help you grip better, and what you're doing is you're increasing the friction between the substance, usually a rubber-made material, and the jar, whatever it's made of, usually metal, or the plastic or whatever, but you're trying to increase the friction. And of course, when you're cold on a nice cold day and you want to warm your hands up, you can just rub your hands together, and sure enough, you produce heat, and we see that certainly friction is a beneficial force there. Another force that we come in contact with is what we call tension force. Sometimes you'll see it described as a stretching force. And there's always going to be tension in a rope and whatever that rope's, the object that's supporting, or that rope's supporting. Ropes always pull. Now again, we say ropes, but we could be talking about a chain. We could be talking about thread. We could be talking about fishing line. We could be talking about bungee cords. There are all kinds of ways that we could apply tension forces. So we always say that ropes always pull. They never push. So when you are pulling a sled through the snow, or you are pulling a fish out of the water on fishing line, you're never using that as a pushing mechanism. It's always a pulling mechanism. And in a single rope, the tension of that rope is the same throughout. So if I have a long rope stretched out and I'm pulling with 5 newtons this way and my friend's pulling with 5 newtons this way, some people would think, well, then the tension in the rope must be 0. Well, if the tension in the rope is 0, then the rope's going to be limp. It's not going to be stretched out and taut. So the tension here would be 5 newtons. The tension here would be 5 newtons. The tension here would be 5 newtons. There'd be 5 newtons all the way through the rope. And that's very important to remember when we get into action and reaction forces in third law. That'll come back. But that's the idea that no matter what, if it's a single rope, that the tension in the rope is the same throughout. Free body diagrams, which you'll hear me call FBDs, are one of the most important aspects of first year physics. It's being good at drawing free body diagrams that allow you to be successful in many aspects of physics. So you talk to a physics student that's in their 3rd year of physics taking that course, they'll tell you that being good at drawing free body diagrams will help you through many physics problems. It is something that initially you think that you can get away without doing a free body diagram, but that is not the case. You must. In mechanics, when you are doing any problems, one of the requirements is that you draw a free body diagram for these problems. So I'll be looking for these in your problems that you're working on in class and turning in. And hopefully you'll become very good at it, because if you become good at these, you'll do well in physics. So what do we use them for? It says used to analyze the forces external acting on an object. Very careful here, the wording. The forces that are acting on an object. It doesn't say anything about the forces that the object is placing on its exterior environment. We are only looking at the forces that are acting on an object. All of the forces are, we're going to say, from the center of the object. So you quite often, when you draw a free body diagram, you typically use a little dot. You don't have to draw a dot in the center, but usually when you draw all your vectors, they'll be coming out of that center dot, and that's just making it easier to understand all the forces acting on it. It would look kind of odd if you drew one here and one out here and one here. It's just easier to understand if you draw it from the center. And again, only draw the forces that act on the object, not by the object. And we're going to go through a bunch of practice ones here and hopefully become really, really good at it by the time we're done with this video. So our first free body diagram, we have a static box. That means a box that's not in motion, and it's just sitting on a horizontal surface. So think of it just like a box sitting on the floor of a garage or on a basement or whatever. The first vector you usually draw with free body diagrams is the weight vector. There are lots of different ways to abbreviate it. I usually use FW when I write it. You could use mg because FW is equal to the mass times gravity, acceleration due to gravity. So if you see me drawing free body diagrams, usually I will be drawing it with a straight down arrow. And you're going to label it FW. Again, you could label it mg. If you want to remind yourself that the weight is always the mass times the gravity, you can do that. Nothing wrong with labeling it like that. And after that, we have to think about, well, what other forces are acting on this box? Well, the other force that comes to mind is this box is static. The box isn't moving. So if there's a weight force being pulled down, and we know this box is at equilibrium, and I know it's at equilibrium because it's not accelerating, we know there has to be a force pointing in the opposite direction. And we said earlier that the normal force is always perpendicular to the surface. So here's our surface, and 90-degree angle to that surface is going to be this direction. So I would draw an arrow. Now, if I'm drawing it to scale, I want to make it the same length as my weight vector, because we're saying that they're in equilibrium, which means that the forces are of equal magnitude. Now, I'm not going to get a ruler out and measure your vectors while you're drawing these, but it is something to think about and does help a little bit to understand the concept of equilibrium. So that's the idea, and you're done. Now, a lot of students want to say, well, isn't there friction? Well, there's no intended motion of this object. There's no one pushing it to the right or trying to push it to the right, or no one pushing it to the left. It's just sitting there, and there's no intended motion for it. So there's no other forces acting on it. It's just the force of normal force from the table or floor or whatever it's sitting on, and the force of gravity, which we call weight, or mg. Our next drawing says a box sliding at constant speed without friction. Constant speed, in this case, it would be constant velocity really, but we can use the word speed if we need to. In this case, it really isn't going to change what we draw. Without friction. Now I said earlier that in this course we deal with perfect world scenarios. So this is a situation where we have to say, okay, even though I know in the real world that there's always friction between a surface and an object, in this case it's telling me that I don't have friction, which means that I'm not going to draw a friction force. Well, what do I have affecting it? Well, I certainly have my weight vector, so I would definitely point that straight down. Always point your weight vector straight down on your page whenever you're drawing it. And again, if you wanted to write mg, that's okay. And is there a surface? Yes, so there's normal force. Which way is the normal force? It's always pointing in a perpendicular direction to the surface. So we're going to draw it straight up, and we're going to try and make it the same distance, same length as the Fw vector. Label it Fn, normal force. And that's it. It's very common for students to think, well, if it's moving, there's got to be some lateral force making it go. Well, that's not the case. Remember, first law, objects like to keep doing what they're already doing. You don't have to have a force pushing an object along to make it keep moving, period. So there is no lateral force here. There's no force making it move to the right or to the left, whichever way we're saying it's moving. All right, so we have a static box with an applied force, and we know it's not moving because it says static, and it doesn't really matter which direction we're trying to move it. We can say it's to the right or to the left. Doesn't make a difference. So let's go ahead and fill out our free body diagram. First thing we want to do, and it's pretty traditional to do your weight vector first. So I'm going to point this down. I'm going to label it Fn. You can label it mg if you want. Oops, not Fn, Fw, for force of weight. And we know that the box is not moving into the ground. It's not being lifted up. There's got to be an equilibrium force that is going against our weight, and that means that we have a normal force, and it's pointing directly opposite the weight. And then our applied force is going to be to the right. Again, I could make it to the left if I wanted. I'm going to draw my applied force to the right. Not very straight vector there, sorry about that. And what is inhibiting our motion to the right? Well, it's friction. And so friction always is parallel to the surface, and it's opposite the intended motion. If we're intending to move it to the right, then we're going to point our friction vector to the left. And because it's at equilibrium, it should be approximately the same length, although that might be a little longer than the force applied vector. And I'm just going to put force of friction. I could put a little s there to represent that it's static friction. And there you have it. That is your free body diagram for static box with an applied force. All right, so we have a static box at constant speed or constant velocity. We do have friction involved, and that's going to cause us to incorporate our different types of friction when we label the vector. So let's go ahead and label our weight vector. We know our normal force vector was going to be directly opposite that, and it's going to be perpendicular to the surface. Straight up, perpendicular to surface, approximately the same length as the weight vector, if you can do that. We're going to be pushing it to the right. That's our applied force. And our motion is to the right, therefore our friction vector is going to be to the left, parallel to the surface. And it's, which type of friction would it be? Well, this object's in motion, so instead of static friction, it's going to be kinetic friction. So if you go back and look at the previous drawing, the only difference between the two is that little K there. If we go back and look at the other picture, it would just be an S for static friction. All right, so this one looks a little different than the first few. This is a box sitting on an incline. We have an angle down here, theta, and it's going to cause us to have to adjust our free body diagrams a little bit, but not a big deal. So let's take a look and see how we're going to handle this. First off, the weight vector. A lot of students want to draw an arrow that way because they think that it's parallel to the ground, but it's not. We always draw the weight vector straight down. So I'm going to draw the weight vector just like that. Label it FW. Or MG, as I've said before. If you want to label it MG, you can. The normal force vector, this is a little bit harder. What we're used to so far is the normal force vector always being directly opposite the weight vector. But in this case, it's not. Weight still pulls straight down towards the center of the Earth, but the normal force vector is still, our rule, perpendicular to the surface of the object. So our parallel surface is the incline, which means our normal force is actually going to point up in that direction. The intended motion of this object, if this box started to slide, which way would it slide? Well, it would slide down the incline. It's not doing that, but if it started to move, it would move down the incline. We wouldn't expect it to just magically start moving up. Which means that we have a friction vector, and we know that friction must always go opposite the intended motion or the motion and parallel to the surface. Parallel to the surface and opposite the intended motion would be that direction. What type of friction is it? Well, it's not moving, so it's static friction. Now this brings up one tiny thing that we have to deal with inclined planes. Because the weight vector is not pulling directly down on the box relative to the surface, that it's sitting on, what we have to do is we have to consider the components of the weight vector. In other words, we have to think of the weight vector as a resultant, a combination of an x and a y component. Well, how long are we supposed to make these? Well, remember, the x and the y component of any resultant always make a 90-degree angle. And you'll learn over time, tend to do this, but you're going to draw the y component for the weight vector first. And it's always going to go from the center of the object. And we usually do our components dotted lines so we don't confuse them with the regular vectors. Now, how far am I supposed to go down? Well, the idea is to make a 90-degree angle. And the 90-degree angle is going to be right here. So this would be what we call my vector. And this would be my little arrow there. This would be my FWX vector. And we see that the FWY vector points directly opposite the normal force. So if this object is in equilibrium, we know that the normal force vector would be the same value as the FWY, the y component of FW. We also know that there's got to be a friction force alternative, meaning something going opposite the friction force that's trying to push the box down the hill. Well, can you see where it would be? It's going to be this FWX. And you'll notice, and I tried to draw it as best I could, the FWX vector, one pointing down the hill, is about the same length as the friction vector. And that's on purpose because you want this idea that they're balancing each other out. And the one last thing to notice is that this angle down here, whatever it is, the angle right here, through the magic of geometry, I'm not going to get into any proofs here, but through the magic of geometry, this angle here is the same as this angle. And that's very convenient when you're trying to solve for your components later on. All right, sliding box with no friction. So again, this is one of those perfect world scenarios where we know there usually is going to be friction, but in our perfect world, we can throw away the real world rules and pretend like we don't have any friction. So we know this box is sliding down the hill, and there's no friction, so I'm not going to draw any friction vector, but there is weight. So let's go ahead and draw our weight vector straight down on the page, just like always. Is there a surface? There is a surface. And if there's a surface, then that means there's a normal force. And we draw it perpendicular to the surface. Excuse me. Perpendicular to the surface, 90-degree angle. Label it Fn. We draw our normal force. We draw our weight components. Again, to draw our weight components, our x and y components, we know that we're going to have our y component point directly opposite the normal force. I'm trying to make a 90-degree angle between my x and my y. There's my y component. There's my x component. So this will be FWY. This will be FWX. And whatever angle this angle is going to be the same. So we notice this mentions nothing about accelerating, but this box has to be accelerating because you'll notice the FWX vector, this vector here, it's pointing down the hill, isn't it? Is there anything pointing against it? Is there anything pointing opposite that vector? There's not. So we have unbalanced forces at work. In other words, we have a net force. And if you have a net force, you always are going to have an accelerating object. And they just happen to be in the same direction. Our net force would be down the hill, and our acceleration would be down the hill in this case. All right, sliding box at constant speed. Doesn't say there's no friction, so we have to assume that there is. So let's go ahead and draw our weight vector. We know that's going to point straight down. Label it FW or MG if you want. We know our normal force vector is going to go perpendicular to our surface, so it's going to go straight up away from the surface of the incline. Constant speed means that it is not accelerating. It's going down the hill, so it's moving, but it's at constant speed, so the object is at equilibrium. And if it's going down the hill, which way are we going to point our friction vector? Well, it's going to go up the hill. Let's go ahead and draw our components first. For the weight vector, again, our y component we draw first. We know it goes directly opposite the normal force. We also know that it's going to form a right angle with the x component. So here's our FWY. Here's our FWX. Now, which way is the friction vector going to point? It's going to point up the hill because the movement is down the hill, parallel to the surface. What type of friction would it be? It would be kinetic friction because the object's moving. And you'll also notice that the vector up the hill is the same as the vector down the hill. In other words, they cancel each other out, so we know the object is at equilibrium. And our angle theta is equal to the angle theta down here. All right, so we have a sliding box accelerating down the hill with friction. Now let's see here. We know we're going to have our FW or mg. Here's our weight vector. We know our normal force is going to be perpendicular to the surface of the incline. We know that friction is going to go up the hill because the box is going down the hill. Let's go ahead and draw the components for our weight vector. And hopefully you can see by now what's going on here. If you think about the weight vector is pulling straight down, not directly down on the surface of the incline. So you could think of it as part of it pushing of the weight force, part of it pushing this way, which is what we call the y component, and part of it pushing the box down the hill. And here's our FWY component, and here's our FWX. And then this is our angle theta. So that's what's going on. The weight vector on an angled plane like this, on an inclined plane, is pulling kind of both ways. You could think of it. You can think of it as pulling down the hill, but also pushing into the inclined plane. Well, this says that the sliding box is accelerating. Now, I know friction is going to be pointing up the hill, but here's the thing you have to think about. If it's accelerating, that means that the object isn't at equilibrium. And equilibrium is when all the forces are balanced. So if I draw a vector of friction pointing up the hill, I want to make it shorter than whatever's pushing it down the hill. Well, FWX is what's pushing it down the hill. That's what's causing it to accelerate. The x component of the weight vector is what's pushing it down the hill. So I'm going to draw my friction vector up the hill, but I'm going to make it a little shorter. And the reason I'm making it shorter is to demonstrate that the friction force is not as great as the x component of the weight. You know, the weight vector, the x component, let's just say it was 5 newtons. Well, I know that the friction force, let's label that friction force. And would it be kinetic or static? Well, it's moving, so it's going to be kinetic. The friction force is going to be less than 5 newtons. So if you have a FWX of 10 newtons, we know the friction force has to be less than 10. It's still there, but because the object's accelerating down the hill, then we know that it's unbalanced forces. So we would say that this object is not in equilibrium. box being pushed uphill at constant speed. All right, so let's take our traditional FW vector and point it straight down. It's always a good place to start. We know the normal force is going to be pointing perpendicular to the surface of the incline, so we'll draw our normal force vector. Go ahead and draw our components for our FW vector, or our y component. Remember, they make a 90-degree angle. So here's FWX, and here's FWY. There's our angle theta. Box being pushed up the hill. Well, if I'm pushing the box up the hill, I'm going to be pushing it with an applied force. So I'm going to push up the hill with an applied force. Well, which way is friction going? Well, the rule is that friction always goes opposite the direction of the object. So in this example, friction is actually going to point down the incline, down the hill. And that's different from our previous examples because we always had friction pointing up the hill. Well, that's because the box was moving or intended to be moved down the hill. Well, in this case, it's going up the hill. And it's at constant speed. And that's another interesting part. We know that this box is in equilibrium. What two forces am I pushing against? Obviously, I'm pushing against friction between the box and the inclined plane surface. But what other vector do you see that I'm pushing against? You may say, well, you're pushing against the weight. Am I pushing against all the weight? Or am I pushing just against the FWX vector because it's pointing down the hill? So the friction vector that I draw and what type of friction is it? Looks like kinetic friction because it's moving. The friction vector that I draw plus the FWX vector, the lengths of these, the magnitudes of these, when put together, should equal the applied force up the hill. So this vector and this vector added together should equal the same length as the applied force pushing up the hill. All right, so we have an object in this case that's not sitting on any surface. It is just in free fall. It's just falling through the air. And the question doesn't mention that we're supposed to incorporate air resistance here. Remember, in this course, we are in the vacuum that we can breathe. So if we see something like a box accelerating in free fall, we ignore air resistance. So I'm just going to draw my downward FW vector, or mg if you want to write that. And that's it. That's all you have to do for a free body diagram like this one. We have nothing that the box is going against because the explanation doesn't say we have to incorporate air resistance here. Box falling at terminal velocity. Well, terminal velocity, this is the idea that when an object is falling through the air, so in this one we have to account for drag or air resistance, whatever you'd like to call it. The box is encountering enough air resistance that it's at a velocity that will not change. So in other words, terminal velocity can be considered constant. And what do we know about constant velocity? Well, if an object is moving at constant velocity, then it is at equilibrium, and all the forces that are acting on it balance out. So if we draw our FW vector, like so, and we're saying that it's at terminal velocity, we have to have some other force going against the weight being pulled down. And it should be the same length as the weight vector pulling down. So this problem, this free body diagram, we would include air resistance. So I'm going to draw a vector approximately the same length as the weight vector. And I'm just going to put force of drag. You could put AR here for air resistance. We don't use it that much in the class, but for this drawing we do need it. Notice that there wasn't any normal force on the previous picture, and there's no normal force here because we're not sitting this box on a surface of anything. So if there's no force, there's no surface, then there's no normal force. All right, so we have a box that's just hanging from a rope or a chain or something like that. And what we're supposed to do here is we're supposed to draw the forces that are acting on the box. Now again, we know that our weight vector is going to pull down like so. And we have to think about what force is preventing the box from falling. Well, it's the force in the rope. Well, what do we call the forces that you get from pulling things with ropes? That's a tension force. So a tension force is what's going against our weight. So we're going to draw a vector directly opposite our weight vector. And I'm going to call it FT, tension force. And that tension force is preventing the box from free falling to the ground. The tension force is always going to follow right along the rope or chain or whatever it's being hung with, the box in this case. It's always going to fall right back up the rope. All right, our last free body diagram is one where we have another box hanging from a couple of ropes this time. So we're going to draw our FW straight down. And we have to think again, what is causing our weight vector to be counterbalanced? What's counterbalancing it? What's preventing it from falling? Well, it's going to be the tension in both of these ropes. But there's two ropes. And you could think of this as kind of a pulley system, or maybe it's wrapped around here. Maybe there's a pulley here, maybe it's being held up, right? And this pulley system is the same rope. So the tension in both of these ropes is what's counterbalancing the force. And because this is straight up and down, we know that's at 90 degrees to the weight vector. And if it's at 90 degrees, the tension is shared by both ropes. So let's say you have a 100 Newton weight. Let's just say that the weight was 100 newtons. Well, that means there's 50 newtons of tension in one wire and 50 newtons of tension in the other. So we just half it. Now, it's only if it's at 90 degrees, right? If it's at an angle, something, like that, where this angle is not 90 degrees, then things change up again. We have to draw some components and things like that. But if it's just at 90 degrees, like this one is, the tension is shared. So if I'm going to draw the tension vectors, I'm going to draw them straight up away from the weight. But because they're the same value, I'm going to try and draw them the same length. And then I would label them FT. Maybe label this one FT1 and this one FT2. But they would both be the same. In other words, if we put both of these together, the lengths, they should add up to the length of this one weight vector. So if this was 200 newtons, then this one would be 100, and this one would be 100. The weights are shared by each rope. And if we had 3 ropes or 4 ropes, then the tension is going to be shared equally. As long as they're at 90-degree angles, it's going to be shared equally by all the ropes supporting it.